Wow. Now that's cold. It's negative 50 degrees Celsius in there. I know it may be hard to believe, but even at this temperature, our Naxtra battery cell can still deliver a stable discharge. And check this out. I can still wirelessly charge my phone with it. Now you might ask, lithium-ion batteries are already so advanced, so why develop sodium-ion batteries at all? Lithium, the key material behind lithium-ion batteries, is often called white oil. Supply is unstable and prices can swing. Those fluctuations eventually affect the end user. Sodium, however, is different. Its reserves are tens of thousands of times more than that of lithium, so scarcity is hardly a concern. Developing sodium-ion batteries reduces reliance at the source, supports a more diversified energy mix, and makes advanced battery technology more accessible. But of course, sodium-ion has its challenges as well. Energy density has traditionally been lower, but last year, when we introduced Naxtra, its energy density increased by 50%. For everyday vehicles, that's more than enough range. But higher range doesn't necessarily mean it's ready for mass production. What works in the lab doesn't always translate to manufacturing. Take moisture sensitivity, for example. During production, sodium-ion battery materials and electrodes can easily absorb water from the air, impacting the lifespan. So we engineered the materials to be hydrophobic, reducing moisture content to below 200 ppm. And then there's the anode. Sodium-ion batteries use hard carbon, which tends to generate gas during production. In just 1 kilo of hard carbon, there can be up to 10 to the 23rd power micropores. If left unchecked, that affects performance. So we developed atomic scale pore engineering with surface moisture retention technology. Without it, the material behaves like a porous brick and bubbles will form in water. With it, the structure becomes more like ceramic tile, dense, stable, and far less porous. And then there's adhesion. The hard carbon anode needs to be coated onto aluminum foil, but bonding has always been a challenge. Our in-house bipolar functional coating solves this like a high-performance, double-sided adhesive layer. And finally, we introduced a self-forming anode technology. Previously, sodium metal would deposit unevenly across the anode. But now, with our adaptive dynamic formation protocol, the electrode undergoes nanoscale structuring, allowing sodium to deposit far more evenly. We've tackled hundreds of challenges like these before. As such, the CATL Naxtra battery can begin being mass-produced at the end of this year. If you've ever hesitated about going electric, or you simply want to try it out, a vehicle powered by our Naxtra battery is a solid place to start.